So this is a unique chemistry of stainless steel that's used in this magnet system.
Well, the heat treatment and the impreg processes are the highest risk. And once that's behind you, then you can relax a little bit.
Our head engineer came up with the main concept. I just kind of finished it up for him. We like this machine because it's worth its weight in gold.
I worked in a metal fabrication shop, and I welded airplanes and cars. I welded a church steeple one time, all different types of materials. It's fun because it's kind of always the same, but it changes daily or weekly, and it being critical is what part I like. It's really important. That makes it kind of makes it more fun.
This magnet project is not a simple commercial transaction. The Berlin laboratory has bought previous magnets, smaller magnets from commercial suppliers where they simply deliver a magnet that meets particular requirements, and that's all there is to it. This project is much bigger. It'll provide a magnet much higher field, a much larger piece of equipment that'll enable them to do experiments nobody else can do elsewhere. Conceptually, we came up with the basic ideas fairly quickly, but you have to prove all those ideas on a smaller scale before you want to build a system this big.
The coil has been half wound already. There's been 8 layers completed of 16. And so what you see here is the completion of layer 8. Right now it's the low field conductor. You see it's got a lot of white cloth. That is S-glass material. That's the insulation. The turn-to-turn insulation is wrapped around it. Once completed, the entire package will be wrapped in glass cloth for all the electrical installation. As we take a look further down, you can see a large payoff spool. That helps provide constant tension as we wind the coil. You can see here, this is a device that we manufactured and designed at the laboratory to help create a uniform wrapping of the insulation, which is pretty important. Since this is a pretty precise wind, we want to have consistent insulating thickness as we wind as well.
And one of the reasons why this machine is so great for our winding line is that it replaced an automated taping head that was as large as three people standing side by side, this tall. When the conduit would go through the center, it would keep on running even though we stopped winding, and it would have too much lag. It was just doing a really horrible winding job. So we decided we need something way better. So we went to then the human aspect, and then we found out that was taking too long, it was too slow, inconsistent. And to fix all that, we built this machine, and everything's been smooth since.
Well, the conduit and the cable inside, very hard to get. We have it built, and it takes several years to have it manufactured. So we just got to take our time, not hurt it, not destroy it. If we hurt this, we can't finish the coil. And this weld, normally, if it was not on something so critical, this would take maybe a minute. But on this, it takes about 3 to 4 hours, start to finish, to do it.
Go for it.
here is a helium penetration. This allows the helium circuit for each layer. And this slows down the winding process just slightly because as we get closer to the end flange, we want to make sure it's critical that this hits in the correct spot, and that even the ramps and fillers that go underneath are also positioned in the correct spot. And so as we wind it in, we take our time, move about 2 or 3 feet per session.
A little bit?
Yeah, a little bit.
Well, yeah, I've been here about 5 months, and previously I was an orthodontic and prosthetic technician and machinist. I also built underwater lights for cave divers and filmmakers, and have been a cave diver for about 35 years. I am building a ramp for the magnet. Well, there's a lot of steps involved in making this. It looks fairly simple, but it started out as a sheet of copper. It was then cut by a water jet. It was then nickel plated. After having the edges deburred and polished, it was then bent to shape in a 3-roll bender to the correct radius of this layer of the magnet. It's now been clamped together and wrapped with fiberglass thread to hold it until we can take the clamps off. It'll then be wrapped with fiberglass insulation just like the conduit on the magnet. It'll then be laid into place, and we'll transition from layer 8 to layer 9 at the helium penetration and send us on our way to winding layer 9.
I'm a full-time student at the engineering school across the street. I have a part-time employment here. I'm able to see on a baseline level what design engineering means. So it's really cool to be able to see on this level and be a part of building something, and then go to school and have the ability to, you know, that's what they need. You know, I'm in class and I get excited because I know layman terminology for what they're actually teaching in the classroom.
So it's a superconducting wire that's twisted to make a cable, and then it's put inside a steel conduit. It's rectangularized and compacted, so at the end you see the cable inside the conduit. Actually 40% void in there, although it certainly doesn't look like it if you were to look at this. This magnet will actually use even less void than this. There'll be about 30% void in the conductors used in this magnet.
It's all very large. It's not a common product, and so in most instances, yes, we build everything, most everything else. Even the furnace system, epoxy impregnation system. Where we can, we'll buy it commercially. It makes things a lot easier, but in those instances where we can't, we'll have to find another solution for that.
This thing behind me, the large brown cylinder you see, is a model coil that is the same inner diameter and outer diameter and built with the same material using the same construction techniques that we'll be following with the production coils. These are irreversible processes, meaning we can't back up and correct them if a problem happens. So essentially, they have to go right the first time. The epoxy that we use was developed here at the Magnet Lab. We developed an epoxy that has a long pot life so that we can let it soak in the epoxy liquid for hours and hours and hours. The other thing it has the mechanical characteristics that are needed so that it won't crack. One of the other difficult aspects of this coil is that it's going to be cooled to 4 Kelvin. And at 4 degrees Kelvin, materials behave very differently, and typically epoxies will crack. Well, this epoxy doesn't. And it doesn't crack because we developed it not to crack.
When it's delivered in Berlin, it'll be unique in the world, providing 25 Teslas initially for neutron scattering. Today the world record's only 16 Teslas, so it'll be a dramatic step forward. And there's the potential to upgrade this magnet to 30 Teslas in the future. And so I expect for at least 10 years they'll have the highest field magnet for neutron scattering worldwide. That's always important in science, to have the capability of doing something that nobody else can do. And one can only really speculate at this point as to what sort of wonderful discoveries will come out of it, but I'm sure the scientists in Berlin would love to talk about their plans.